Welcome back to the deep dive. Today, we're not just reading the manual, we are really getting under the hood of hardware engineering. We're going to explore one of the most, I think, elegant solutions in modern digital signal processing. So, if you're getting ready for a meeting on next gen chip architecture, or you just love seeing how, pure math meets the physical world, this is definitely one for you. Our mission today sounds, well, on the surface, it sounds deceptively simple. We're looking at how engineers are able to achieve really high performance signal filtering,
Right?
and specifically the design of something called multiplierless FIR filters.
Mm-hmm.
Now, if that just sounds like jargon, the core idea is basically cutting the cord to the most expensive element on any chip.
The multiplication circuit.
Exactly. We want all that performance, but without the power drain, without the space hogging, or all the heat that comes with it.
That is the absolute core of the challenge. I mean, in digital signal processing, you rely so heavily on these FIR filters, finite impulse response filters.
We're everywhere.
They're everywhere. Think of them as like the ultimate acoustic equalizer for your signal. And traditionally, every single time you apply a coefficient to your data stream, you need a full multiplication operation.
You just do multiply, multiply, multiply over and over.
Over and over. Multiply by 0.5, multiply by 0.25, and all those little multipliers, they pile up, they demand huge amounts of silicon real estate, consume a ton of power, and just drive up the complexity and the cost of the final chip. So, the breakthrough that we're diving into today, it replaces that expensive, power-hungry multiplication entirely.
Just gets rid of it.
Gone. We substitute it with really simple, cheap binary shifts combined with just basic addition and subtraction.
Okay, but to do that while keeping the signal quality high, that sounds tricky.
It is. To achieve that level of optimization, the design framework has to brilliantly integrate three really powerful and necessary techniques.
All right, so we need to know what's holding this whole architecture up. What are the three core pillars that let us, cheat the cost of multiplication?
You need foundational math, a hardware trick, and then sort of an intelligent orchestrator.
Okay.
So first, there's spectral factorization theory. That provides the rigorous mathematical guarantee. It ensures we derive a stable filter that actually works correctly.
It's the theoretical backbone.
Precisely.
Yeah.
Second, the crucial hardware optimization. Canonical sign digit, or CSD, representation. That's the actual mechanism that lets us eliminate the multipliers.
The trick.
That's the trick. And third, advanced convex optimization using the ellipsoid method. And that's the tool we use to tune everything to make sure the final design meets all of those rigorous, real-world demands like signal purity and stability.
Let's start with that hardware trick then, pillar 2, the multiplier dilemma. You called it the expensive circuit. It's bulky, it's slow, it's hot. So the question is still, how do you multiply without multiplying? It just sounds like you're trading one kind of complexity for another. Aren't we just building a huge array of smaller adders instead of one big multiplier?
That is a really fair and important question. And if we were just breaking down multiplication using standard binary, you'd be absolutely right. We'd just be shifting complexity around. But we're not using standard binary. We are optimizing the representation of the numbers themselves for hardware efficiency. And we do that using canonical sign digit CSD.
Okay, CSD, what is that exactly?
It's a sign digit number system.
Yeah.
So instead of standard binary where you're only using zeros and ones, CSD uses digits from the set, -1, 0, and +1.
-1, 0, +1.
Right. And the genius of it is that when you multiply by a coefficient represented in CSD, that entire multiplication operation gets replaced by a small, fixed number of simple binary shifts.
Which in hardware are basically just wires. They're almost free.
They're incredibly cheap, yeah. And you combine those with simple addition and subtraction operations.
So we've effectively swapped this big, complex multiplier block for a handful of really simple adder and subtractor circuits. That sounds like a win already, but what really makes CSD so much better than just saying, okay, we'll use binary shifts and adds?
The key term here is sparsity.
Sparsity.
CSD representations are intrinsically designed to maximize the number of zeros and minimize the number of non-zero digits, so the +1s and the -1s. This sparsity, that's the real key to the massive hardware savings. Fewer non-zero digits means you need fewer additions and subtractions in the physical circuit.
Okay, so you're actually reducing the number of operations required.
Dramatically. I mean, think about the physical chip layout, A traditional fixed point multiplier is this dense, high gate count circuit block. When we use CSD, that whole dense block just vanishes. It gets replaced by a sparse array of simple adders and shifters. Sparsity translates directly to simpler, smaller, and cooler hardware.
Can you give us a quick example of that, just to visualize the sparsity? How much simpler are we talking?
Yeah, absolutely. Let's take the decimal number 0.875. In standard binary, that's a 0.111, three non-zero digits.
So 3 operations.
Right. That means 3 additions or shifters and adders would be necessary. Now in CSD, that exact same number is represented as 1.00 minus 1.
Ah, so you've gone from 3 non-zero digits to just 2.
Exactly. O plus 1 and a minus 1, which means you only need 2 add or subtract operations. We've dropped a full operation just by changing the number system. And the beauty is that the CSD conversion algorithm is deterministic. It always finds the sparsest possible representation for our coefficients.
So we've nailed the hardware trick. We know how to make the circuit cheaper and more efficient using CSD. But, a cheap filter isn't very useful if the math behind it is shaky. So how does Pillar 1, this spectral factorization, step in to give us that essential guarantee of stability and correctness?
That's where we bridge that gap between optimizing the hardware and rigorous signal processing theory. Because eliminating the multipliers and converting to CSD must not compromise the theoretical correctness of the filter, especially its phase behavior.
Okay, so what's the objective here with spectral factorization? What are we trying to achieve?
The goal is to derive a stable minimum phase impulse response, we'll call it HK, from a given autocorrelation sequence, ERK.
In plain English, what does that mean?
So ERK basically represents the essential frequency characteristics of the signal we want to filter. It's the what. The impulse response, HK, is the actual sequence of coefficients that creates the filter. That's the how. And minimum phase is critical. It means the filter is stable and its energy is concentrated at the earliest possible time. That's essential for low delay, high quality signal processing.
What's really fascinating here is that the mathematical underpinning isn't some brand new cutting edge algorithm. You're actually relying on some pretty classical work.
Indeed. The core foundation relies on the Kolmogorov 1939 approach. It's this brilliant piece of mathematics that was originally developed for, stationary time series and prediction in analog systems.
But now it's being applied to digital chip design.
Exactly. Our implementation uses a really robust 4-step process to ensure we get numerical stability and precision when we're converting that raw data into a set of usable coefficients. So step 1 is oversampling. We typically oversample the autocorrelation sequence maybe by 100 times to smooth out the data. This significantly improves numerical stability and prevents errors down the line.
Right.
Step 2, we use the fast Fourier transform, the FFT, to shift that oversampled sequence into the frequency domain, where it's just much easier to analyze.
And this leads us to the really critical step, right? Separating the magnitude and phase. That sounds like where the rubber meets the road for that minimum phase design.
Precisely. Step 3 is applying the logarithm and the Hilbert transform. The logarithm operation, it transforms the product of magnitude and phase components into a sum, which means we can separate them.
Okay.
Then the Hilbert transform acts as this kind of mathematical lever. It allows us to derive the minimum phase component just from the magnitude information. This really is the heart of generating a filter that is physically stable and predictable.
And then the final step.
Finally, step 4 is the inverse FFT. It just brings our derived minimum phase impulse response, our HK, back into the time domain, ready for the next stage.
Okay, so we've got the rigorous math foundation from Kolmogorov, that's Pillar 1, giving us a stable starting point. And we've got the powerful hardware trick using CSD, Pillar 2, giving us efficiency. But here's the challenge I see. The spectral factorization gives us this continuous theoretically perfect filter. But CSD forces those coefficients to be discretized. They can only be represented by a few -1s, zeros, or +1s. That discretization has to introduce errors, right?
It absolutely does, and that is the critical juncture. How do we find the best possible set of CSD coefficients that keeps the hardware cheap and still respects the necessary signal quality? And that's where Pillar 3, the orchestrator, comes in. Convex optimization using the ellipsoid method.
Right, the system that balances everything.
Exactly. Filter design is inherently a high-dimensional convex optimization problem. We're searching for an optimal set of CSD coefficients that satisfies many and often conflicting design constraints all at the same time.
So if you satisfy the hardware constraint, like low CSD digits, you might violate a performance constraint, like having too much ripple in your signal. We need a tool that can navigate this trade-off space intelligently.
What are the core constraints that this tool has to manage? Give us the real-world performance metrics.
Well, the list is rigorous. We are talking about controlling the passband ripple. That's how flat the signal stays where we want it to work.
Hmm.
We have to ensure sufficient stop band attenuation, how completely we silence the noise outside the desired frequency range.
Hmm.
We need non-negative real requirements, which means the filter has to be physically realizable. And critically, we have the CST digit limits, which directly control the cost and complexity of the hardware. The ellipsoid method is our iterative search engine. It starts with this vast search space represented by an ellipsoid, and in each iteration, it systematically shrinks that space. Okay.
It just keeps eliminating areas that don't satisfy all the constraints until it converges on a small set of coefficients that achieves the best possible balance.
And the power of this method relies on an internal quality control system. You call it the oracle. What does that do?
Think of the oracle as the ultimate QA system for the filter. For any given set of tentative coefficients you feed it, the oracle instantly determines if a constraint has been violated.
So it's a pass-fail check.
It's more than that. If, for instance, the passband ripple is too high, the oracle doesn't just flag the violation, it provides the necessary mathematical guidance back to the optimization algorithm. It tells it exactly how to adjust the search space, how to shrink the ellipsoid, to find a better solution in the very next step.
Now, I understand the standard ellipsoid method, but I see this framework uses an advanced capability. It supports something called parallel cuts. Why is that so powerful in this context, with all these competing constraints?
Oh, it's a crucial accelerator for any real-world design. Often, a set of coefficients might violate 3 or 4 constraints at the same time.
Right. Too much ripple, not enough stop band attenuation, too many CSD digits.
Exactly. A standard method would have to address those one by one, which is slow. Parallel cuts allows the algorithm to tackle multiple constraint violations simultaneously in a single iteration. This dramatically speeds up convergence and is absolutely essential for complex, multi-objective optimization. It helps us find that sweet spot between cost and performance so much faster.
Okay, let's put all three pillars together now and look at the complete design flow. This is really where the spectral factorization, the CSD trick, and the ellipsoid method become one intelligent, iterative framework.
It's a cyclical flow, yeah. It starts with an initial filter design based on whatever specifications you need. That design immediately goes into the rigorous spectral factorization step to ensure it's minimum phase and stable. That gives us our mathematically sound, continuous valued coefficients. Then, those coefficients are processed by the hardware-friendly CSD conversion.
And that CSD conversion, the step that makes the hardware so efficient, is also what inevitably introduces the error that kicks us into that iterative optimization loop.
Exactly right. Once CSD conversion is done, we hit the oracle assessment. The oracle checks every single constraint. Path band, stop band, CSD limits, all of it. If the oracle finds a violation, let's say the CSD conversion introduced too much error and now our stop band attenuation is compromised, the constraints are updated in the optimization engine and the search space, the ellipsoid, is modified.
So you don't go back to square one.
No, you just refine the search. You use the guidance from the oracle to keep narrowing down the possibilities until all constraints are satisfied.
And this cycle just keeps going, updating parameters, running the oracle assessment until the system checks for convergence.
That's right. And once that ellipsoid has shrunk down sufficiently and all of the constraints hold true, we have our final filter design. And that final design delivers just enormous hardware advantages. I mean, we've managed to avoid multiplication, but what's the real world consequence of that?
Well, the results are extremely tangible and practical. First, you get reduced complexity. You're replacing these dense multiplication circuits with simple adders and subtractors, which simplifies the whole chip layout. Secondly, lower power consumption. We said it before, multiplication is a massive energy sink. Removing it leads directly to highly energy-efficient DSP designs.
And that efficiency doesn't just stop at size and power.
Not at all. We gain significant faster execution because, well, addition and shifting are just fundamentally quicker operations than a full multiplication. But for real-time applications, I think the most critical benefit is deterministic timing. Because the execution time is dictated by that fixed, sparse CSD structure, the filter speed becomes predictable. It's independent of the specific data or coefficient values. And that is absolutely vital for high reliability systems, like medical imaging or aerospace applications. We've seen the frequency response plots, the ones comparing the continuous filter, the ideal math, to the final multiplierless CSD filter, the cheap hardware. Which metric on that plot really confirms that this multiplierless design is truly successful and not just, a cheap approximation?
You have to look at two things: the passband flatness and the group delay. Passband flatness shows we haven't lost signal fidelity where it counts. That's important. But the group delay matching is really key.
Why is that one so important?
Group delay measures how quickly and uniformly all the different frequency components of the signal arrive. If the group delay of our CSD filter closely matches the ideal continuous filter, it confirms we've achieved that necessary minimum phase stability and the time domain predictability, all without the hardware cost. That comparison proves we gained hardware efficiency without sacrificing that crucial signal integrity. This whole project, the combination of, classical Kolmogorov spectral factorization, ensuring stability, the hardware efficiency of CSD representation, and the modern optimization power of the ellipsoid method, it really stands as this profound testament to successfully adapting advanced mathematical algorithms to meet very practical, very stringent hardware constraints.
It's a beautiful example of using rigorous theory to achieve simplicity in silicon.
It really is.
In this framework, it seems like a fantastic starting point for future developments. What's next on the horizon for expanding this approach?
Oh, if we connect this to the bigger picture, the foundation is really set. We can extend this methodology immediately to higher order filters, longer, more complex impulse responses. We could develop real time implementation capabilities for adaptive filtering, where the filter actually changes its properties on the fly.
That's a big one.
It is. And crucially, the deterministic CSD output is just perfect for automatic hardware generation. We can synthesize Verilog or VHDL chip descriptions directly from the optimized CSD coefficients.
So straight from math to chip design.
Essentially. And finally, extending the system to support multi-band extensions for applications that require really complex signal separation.
It truly shows how mathematics can be used to drastically simplify the physical world. As we wrap up this deep dive, I want to leave you, the listener, with a final thought, built around that CSD system and its reliance on sparsity. Given that CSD only uses the digits -1, 0, or +1 to represent coefficients, which of those three digits do you think is the most valuable when you're trying to optimize for hardware efficiency and cost? Think about which digit requires the least amount of physical activity or wiring on the chip, and what that optimization framework is so aggressively trying to maximize. Ponder that simple but pretty profound question of zero-cost optimization as you go about your day. Thanks for diving deep with us.